Before we get started with the video, I do want to say I'm working on a video for the 2025 MIT Integration B Finals. That will hopefully be out soon. But in the meantime, hello everyone and welcome back to another Physics Friday, where we are going to be going over the Euler-Lagrange equations. We'll hopefully be using these next week to do some cool stuff with deriving Coulomb's law, but I am getting ahead of myself. In the meantime, let's get focused on these right here. So what exactly are the Euler-Lagrange equations? Well, the Euler-Lagrange equations are a bunch of equations, a set of equations really, and what they do is they describe the conditions for an extrema given some functional. So in physics we have something called the action, which is denoted as S, and it's an integral over our Lagrangian. In this video we're actually going to be using a Lagrangian density, so we're going to write that as fancy little L, and then we're going to integrate over all space and time, so d4x. But the idea of the Euler-Lagrange equation, again, is to basically find the conditions under which this right here is minimized, because the equations of motion in physics result from when the Lagrangian is, or Lagrangian density, is minimized. And we do that through the Euler-Lagrange equations. So let's go ahead and actually derive them. What we're going to assume is that our Lagrangian is a function of some field phi, and also a function of its first derivative, so partial mu phi, and then we're also going to assume that it's a function of all of its second derivatives, so partial nu, partial mu phi, and so on and so forth. That's what we're going to be assuming our Lagrangian is a function of. And what we're going to assume about phi right here, is that it satisfies this integral being an extrema, or since it's an action, a minimum. And since it is going to satisfy that, let's take an idea from calculus and kind of apply it here. And that idea is a small little perturbation. What we're going to say is that phi is going to basically turn into phi plus some little delta and then plus some small field perturbation nu. So what we're going to do is consider our Lagrangian for this right here, but where our phi is really this right here and contains a small little perturbation. So let me rewrite that real fast. And as is typical in calculus, what we're going to do is actually just take the limit as this delta goes to 0. As we just turn off the perturbation, because we are assuming that this phi does indeed make this action right here, this integral over our Lagrangian density, a minimum. So what we're going to do is take the derivative, or partial derivative of s, with respect to this delta right here, and set it equal to 0, because this is the same idea as finding the minimum or maximum of just some function. If we want to find the local minima or maxima of some polynomial function, what we would do is just, differentiate it with respect to like x, and then just set it equal to 0. And that's basically what we're doing here. We're differentiating with respect to this delta, this small kind of perturbation constant, and then we're just going to set that derivative equal to 0. Because if this function phi does indeed cause this action, or this integral over our Lagrangian, to be a minimum or maximum, a small change in it should effectively be 0, right? So let's go ahead and do that. So we have the partial derivative of our action right here with respect to our delta, and we're going to set that equal to 0. But what exactly does that equal? Well, that's going to equal, so the integral over space-time right here. But then we also have our partial derivative. So we have partial, and then our Lagrangian, and then with respect to our delta. And now this is the part where it gets interesting, because what we're going to do is apply the multivariable chain rule on this a bunch. So let's see what we get. What the multivariable chain rule tells us is that if we differentiate our Lagrangian with respect to some delta, then the result is just going to be the partial derivative of our Lagrangian with respect to the different arguments of our Lagrangian. So I'm just call that q. So qj, and then times the derivative of those parts of those arguments of the Lagrangian with respect to our original delta. Q1 would just refer to this phi plus delta nu right there, that whole first bit. And then Q2, for example, would refer to this whole term and so on and so forth. This right here is just going to be, well, let's consider Q1. So we have the partial derivative of our Lagrangian with respect to Q1. And as we just said, that's partial and then phi and then plus delta nu. And then we're going to have the derivative of this right here, phi plus delta nu, and then with respect to our delta. But we're assuming that the function that minimizes this isn't actually a function of delta at all. So this right here is just going to be 0. And the partial derivative of delta nu with respect to delta, well, that's just going to be nu itself. So although we have more terms, let's go ahead and simplify this right here. So we have nu and then times our the partial derivative of our Lagrangian, and then with respect to phi plus delta nu. Okay, great. Now, what exactly is our second term here? Well, taking a look at our Lagrangian, we're going to have plus, obviously. I'll write the plus in a different color. That's fun. I need to play around with colors more. But we have the partial derivative of our Lagrangian as before, but then with respect to this right here. So with respect to all the partial derivatives of this, so phi and then plus delta nu. And then we're going to have the partial derivative of the partial nu. Partial derivative, partial nu, of then just phi plus delta nu. And as is the case, and yeah, we are differentiating with respect to delta, but as is the case for partial derivatives, you can reverse the order and you're going to get the same result, at least for us. So what we're going to do is simplify this term right here, and what we're going to get is going to be a bunch of partial derivatives of nu. So to actually write that out, it's going to be partial mu and then times nu. So writing out everything that we have, we're starting to see a pattern form, but let's do this one more time just to really hammer that in. So remember the next term in our Lagrangian, so I'll try it down here so I don't have to keep scrolling. So Q2 is just going to be equal to the double partial derivative now, so partial nu, partial mu, phi plus delta and then nu. So what does our multivariable chain rule tell us? Well, it says that we're going to have, well, a plus first off, and then it says we're going to have the partial derivative, so partial derivative of a Lagrangian with respect to, well, this right here, so partial nu, partial mu of phi plus delta nu. That's a mouthful, oh my goodness. And then what we're going to have is going to be the partial derivative of this right here, so partial of phi plus delta nu with respect to just delta. And as before, this is just going to simplify to partial nu, partial mu of nu. So erasing and rewriting. And it's at this point you can really start to see a clear pattern. In the first one right here, in the first term, we had no additional derivatives. We're just differentiating with respect to our field, phi, and plus the perturbation, obviously. But then for our second one, so for this one right here, we did have one derivative, and what that gave us is an extra derivative with respect to nu. And you see that we have a similar thing again, right here, where we're taking two derivatives of our field, and then it's being multiplied by two derivatives of our extra little field perturbation. But it would be awfully nice, for reasons I will explain shortly, just to get all these nu's by themselves, because that way we could factor it out and then just get a term with a bunch of our Lagrangians. So really there should be a plus dot 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 here actually, because we do have additional terms. How exactly can we get rid of the derivatives on these new terms right here? And the answer is integration by parts, because you'll remember, from Calc 1 or 2 or something or the other, that if we have the integral of f times g prime, then with respect to x, then we have this is equal to fg, and then minus the integral of f prime g, and then with respect to x. But what we're going to assume, as is the case for many things in physics, is that the edge cases, or these right here, are just going to be 0. That as our fields go out to infinity, those there are just going to be 0. So we can really just focus on this bit right here. And perhaps you aren't completely convinced of this. And to that, I will direct you to the wonderful textbook I am reading on the subject. Would totally recommend. But what we're going to do is effectively just transfer these derivatives right here onto our Lagrangian term right there. That way we can just factor out our nu. So applying integration by parts a bunch, this right here is what we obtain. So if we factor out our nu, what we end up with is going to be our big integral on the outside with respect to all spacetime, and then we're just going to have our big nu, so adding some parentheses, we're going to have our big nu out front right there. And this is the part where we are just going to basically just turn off our perturbation. We're going to say that our delta is just going to equal 0. So what that does is just eliminate all of these delta nu terms in the partial derivative. So we can just get rid of that right there, and get rid of this right here. And that cleans things up actually quite a bit. But one thing that we did assume is that in our perturbation, so we assumed that our phi became a phi and then plus some delta nu. What we assumed is that this nu right here, implicitly, is just not 0, because otherwise, if nu is 0, then really this delta can be anything, and this doesn't really affect our function or our field right here. So what we do is we assume a non-zero nu. The only possible way for this integral to be 0 is, if this isn't 0, is for all of this right here to be equal to 0. And that right there, ladies and gentlemen, are the Euler-Lagrange equations. So these right here are the Euler-Lagrange equations. But what exactly is the pattern right here? What exactly is the pattern here? Well, we see more or less that the number of derivatives we're differentiating our Lagrangian with is the same number of derivatives that whole term is being differentiated by. So one derivative there of our field, and we have two derivatives here. You see that we have one derivative there of the term and two derivatives there of the term. So in general, what we have is we can express this as just a sum, right? And then, of course, negative ones can be taken care of by just a negative 1 to the k term, for example. So what we have is just a sum from k equals 0 all the way up to n minus 1, whichever degree of derivative our Lagrangian happens to be a function of. And we see that we just have partial, say, call it alpha 1, and then partial alpha 2, and then dot, 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 all the way up to partial of alpha k. Where there are implied sums over alpha 1 to all the way up to k. And then we're just going to have times, or not really times, but those derivatives are going to be acting upon the partial derivative of our Lagrangian. And then that's being differentiated with respect to, well, all that right there, what we wrote up front. So partial alpha 1, partial alpha 2, dot, 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 all the way up to partial alpha k of our field right here. And then we will throw in our negative 1 to the k term just out in front, because that comes with our integration by parts. And these right here are just the generalized Euler-Lagrange equations for fields. Now, one thing that I do want to do, and I think this is actually quite interesting, is take this right here, this form of the Euler-Lagrange equation, and just get the one that you first learned about, the one that you know and love, that you maybe derived the brachistochrone with, or the catenary. Let's get that just in terms of maybe just time in one function, right? One of the parallels here is that our field phi is actually just one way to say f, some function that satisfies conditions right here. So one way we can rewrite this first term is just going to be partial r Lagrangian, and then differentiate that with respect to f. And then we're going to have minus, well, partial mu. But whenever we have like a 1D Lagrangian like this, it's not so much a Lagrangian density as it is just a normal Lagrangian. And typically in that case, what we're doing is we're integrating our Lagrangian, but just over time. So because of that, the only coordinate we have is time, really. So we're differentiating this with respect to t. And then what we have is, well, the same thing as before, but we're going to have the time derivative of f now. So we're going to have partial our Lagrangian, and then partial f, and then dot for the time derivative. And that right there is going to equal 0. And it should be noted here that all this does equal 0 right there. I forgot to add that. But anyways, I hope you all enjoyed this, a little bit of a different video, deriving the Euler-Lagrange equations, and I hope to see you all in the next one. Thank you for watching.